Hi everyone. Hope everything is well with you so far in this term. Uh, in this part, I'm going to show you how we can implement the simulation of the multi-server model in in Excel. Okay, so here we have the data of the problem, the interval time for customers. It could be 1 minute to 4 minutes. We have the probabilities and we can calculate the CDF or cumulative probability function for interval time of customers. Okay, and the same as interval time, we have the discrete function for Abel's service time and also Baker's service time. And again, with the same manner of interval time, we can calculate the cumulative probability function by just adding up the probabilities. So calculate the CDF for Abel's service time and Baker's service time. Okay. And here we have the total number of customers as 100. So we are going to simulate the system for exactly 100 customers. Okay, so since we track the customers individually one by one, so each row will be for a customer. Okay, so the first row is for the first customer, and by the definition, the first customer arrives the system at time 0. Okay, so you don't need to generate interval time for the first customer, so it's 0 by the definition, and so interval time is at 0. And again, by the definition, both servers are free and available at time 0. So the earliest available time for Abel and Baker is 0. Since both are available, and again, by the discipline assumption that we have in this system, when both are available, Abel will take the call. So here, Abel is assigned to this call. Okay. And for service time, we need to generate a random variable considering the discrete distribution of the Abel's service time. Okay, and you see how we do this. But there is a simpler way than this one, which you can use the discrete EMP for empirical distribution, this discrete empirical distribution function. In order to use that function, you need to run the Visual Basic file that is available in the BCNN folder in Learn. So by having that file, you can use that function, and you can generate the random variable in much easier way. Okay. So the waiting time for the first customer would be 0. The service start time is 0, and the service end time is service start time plus service time. Here 0 plus 3 will be 3, and busy time of server A will be 3 minutes. Busy time for server B here is 0 for this customer, and service start of server A here is again 0, and service end of A is 3, and we have no data for Baker, right? Yet. So that's for the first customer. For the second customer, for the interval time, in order to obtain the interval time of the second customer, we need to generate an interval time at first. So here we generate a random variable again by the discrete distribution that we have for interval time. So here, as you see here, it's 3 minutes. So this means that the second customer will arrive at time 0 plus 3, which is time 3, right? And since Abel is going to be free at time 3, so the earliest available time of server A is 3, right? And the earliest available time of server B, Baker, is 0 as well. So this means both will be available at time 3 to serve the second customer, right? Again, since both are available, we need to assign Abel to this call. So Abel will be the assigned server for this call. As you see here, how we actually obtain which server should be assigned to this call. Actually here I just implemented exactly the relation that we have in the lecture notes. So just follow those equations and relations and just implement those relations here in Excel, and that's it. There's no difference between the functions here and the ones that we have in the lecture note. Okay. And again, with the same manner, we generate the service time for this customer from the Abel's service time distribution. And again, there is no waiting time for this. For the waiting time will be the maximum between 0 and J14 minus D14. So what's J? J here is the service start time, and D here is the arrival time. Yes, the service start time minus the arrival time will be the waiting time, and if it's negative or it's 0, so we take the waiting time as 0, but if it's positive, it will be the waiting time. Okay. The service start time will be again the maximum between two quantities. D14, D here is the arrival time, and between the minimum of E and F. So E here is the earliest available time of server A, and F is the earliest available time of server B, right? Yeah. So here we have this service start time, and again, services end time will be service start time plus the service time, and so again we can easily calculate the busy time of server A here, and so on. Yeah, so we have the same relations for 100 customers. Okay, and at the end we can calculate the system's performance here. So we have the total minutes of working time for server A, total minutes of working time for server B, and the duration of total service time, utilization rates for server A, server B, and average waiting time here is 0.65 minutes. Maximum waiting time is 5 minutes, and the number of customers who wait is 37 out of 100. So the probability to wait is 0.37, right? And here we have somehow the histogram for the waiting times. Okay, but this is just for one trial. I mean, just running the simulation model for 100 customers. But we have here the impact of randomness, right? And in order to decrease the impact of randomness, we have two approaches: increasing the number of customers from 100, let's say, to 1,000 or 10,000, 100,000, and so on, or having replications. I mean, we can replicate the simulation of 100 customers 4,000 times, for example. Okay, this is what we have done it here. So in the third sheet here, we have the experiment. So we have 1,000 replications. This means that we are replicating the simulation of 100 customers 4,000 times. So by doing so, actually, we are mitigating somehow with the impact of the randomness, right? And let's say our measure here is just the average waiting time, and this is 0.588, right? And this is somehow the histogram of the average waiting time in total. So as you see here, the average waiting time is somehow a random variable, and we have a distribution for that, right? We can fit a statistical distribution for the average waiting time. We will see how we do this in chapters 11 and 12. So, but until then, just consider this the concept just average waiting time. Okay. So the only reason that I have a refresh button here is to show you how the results are sensitive to the number of replications. For example, here when we refresh the numbers, you see how the results are changing dramatically, right? For example, in the previous round, the number of customers who wait was 37. Now it's 50, right? And the average waiting time now it's 0.81 minutes. And again, if I press the refresh button one more time, you see again different numbers. Average waiting time is 0.45. Wow, 45. And the number of customers who wait is 29. See? So as you see here, the results are not stable. So we can't rely on the result of having just one trial of the simulation. In order to decrease this randomness impact, we have to have replications, right? This is why we have 1000 replications here. And if let's see here, this is the average waiting time is 0.58, right? Let's do refresh one more time. It becomes 0.6. It's still changing, right? But the change range is not too much. Right? It was 0.588, now it's 0.6. Let's press one more time. Now it's again 0.587. See, now we can say the results are much more reliable, right? And we can have a better and more confident insight of these results. Okay, so this is why we do the replication. Okay, so in the second sheet, you see how we can actually draw the number of customers in line, just the queue length. Okay, and that's it. So yeah, this was for the multiple server queuing system, and I'm gonna have the other parts in Excel in order to show the rest of the models. Okay, thank you.